Begin by thanking David and ICAM for inviting me here. Is that sounding? Is my voice loud enough?
It's good.
Okay.
Right.
Because you're all tired and I only have 15 minutes to explain this to you, I'm going to be quick. So the idea is it possible to use Mott insulators to produce photovoltaic effect, and is it efficient, and is it a good idea? So I'm going to try to be brief. First of all, what's wrong with, briefly, with traditional band insulators or semiconductors? So if a solar photon comes and hits this material which has the occupied states and the empty states here, and photoexcites an electron-hole pair, because the solar spectrum is very broad, starts from, let's say, half an electron volt all the way to 3.5 electron volts, no matter what semiconductor gap you choose, if the gap, for example, is relatively small, half this range or something like that, then you excite sometimes electrons or holes with energy significantly above the semiconducting gap, and so the excess energy delta E will eventually be lost by either phonon emission or through electron-phonon scattering, and the excited electron or hole is going to land eventually to the band edges in about 10 to the minus 12 or 10 to the minus 13 seconds because of this mechanism. If instead to avoid these hot electrons, you increase the gap, then you cut off most of the solar photons. And so if you try to use cascade multiple PN junctions, this is, as mentioned earlier, an expensive way to increase efficiency. So the question is it possible to use some other material which can be, number one, used for the, you have to demonstrate the photovoltaic effect for those, and is it efficient? And so everybody in strong electrons knows about this class of materials, but I'll mention briefly, very quickly, what they are for the other people. Pars and Mott, about half a century ago, explained why materials which are supposed to be half-filled, and because they are half-filled, the band is half-filled, it's supposed to be conductor according to band structure calculations, because there are states available next door for the electron to move. There are a class of materials which they were actually at half-filling, they were perfectly insulating. And so Mott and Pyrrhus said that perhaps this is caused by the fact that when the electrons try to move next door, you create a double occupancy, and that's costing you a lot of Coulomb repulsion energy. So this is basically limiting the conductivity. Unless you go just above half-filling or just below half-filling by introducing donors or acceptors. And so you create basically electrically neutral materials, of course, but doubly-occupied sites in this strong coupling picture, or holes. And so I'm going to, all my thoughts here will be expressed within this kind of framework of the strong coupling, if you like, one band Haber model, just to describe only the idea. This is not realism, but it's just a framework to conceptualize this idea. So then, because of this strong Coulomb repulsion, the on-site repulsion, you pay an energy cost, and so what we call here one W occupied site, one hole state, which can be photoexcited, separated from the ground state by a gap, which I denote here by U star, and then because you can move these W occupied sites around and the holes around, there is a bandwidth, and then you have states also separated by some gap, which correspond to two W occupied sites, two holes, and so forth. Now, if you try to make an junction between a Mott insulator, which is p-doped on one side, and an n-doped Mott insulator next door, here you have already, for this material, you have to pay the price because you are above half filling to create these double occupancies. Here you have holes because you are below half filling, and in fact both sides are electrically neutral. But because of this extra cost here, this extra energy cost can be relieved by having this hopping of this extra electron to the other side with the goal to reach the hole. And so you basically leave behind now a singly occupied side, so you gain U, but you have created a charge carrier, a charge side behind, and you have created, this is a positively charged atom or side, and then you have created negatively charged there. As a result, you create an electric field across this interface. And this develops until the point where the electron to cross on the other side has to overcome that field, that developed field, and that gain, that cost is going to be of the order of this energy on side, the gap, the Coulomb gap or the Mott gap. So you develop this electric field across the interface, and so if a photon comes in now and hits one side, by the way, this doesn't have to be both Mott insulator. I need only the illuminated side to be a Mott insulator, at least. So a photon comes in and can create a particle, a double occupied side and a hole, and forces are oppositely charged, and because of the existence of this electric field here across the interface, if you join this with leads, as was explained earlier, is going to separate this electric field here, is going to collect the carriers in the opposite sides of this device, and so you're going to have a photocurrent. Now, is this an efficient? So you can have a photovoltaic effect, and I will explain to you that quite recently this has been demonstrated experimentally. But so it's not just a conceptual game, but I'm going to also demonstrate to you this can be very highly efficient for conceptual reasons. This hasn't yet quite demonstrated in practice. So if you choose a narrow band, a narrow gap Mott insulator, I'm going to work this for both cases: narrow gap, a narrow band, and wide band, and narrow gap. But the narrow gap is crucial. In the abstract, I was only discussing narrow gap and narrow band, but this has been generated since then to also the case of wide band. So I'm going to discuss here two cases: narrow band case and wide band. So in the case of narrow band, so I have a narrow band Mott band. This is the first Hubble band. This is the second, the other Hubble band. And I have both narrow gap. By narrow, I mean of the order of half an electron volt, small compared to the spectrum, the solar spectrum, and then the band also that size. But I also, because of the existence of highly energetic solar photons, if I have a photon coming in and this photon excites an electron hole pair, if this is highly energetic, the electron is going to land in some empty band. There's lots of spaghetti around this material, in principle, from uncorrelated bands. So there is place for this electron to land in this photoexcitation. So, but as I will show you in the next transparency, this highly excited electron can land in this Mott in the upper Hubble band, and give this extra energy here into creating another pair of electron hole excitation from the Hubbard insulating state. So I can understand this from going back to the strong on-site limit by having the photon coming in. Here is the atom with, this is the Mott state, the state that produces the Mott, many bands of Mott. But then this is highly excited state, another state here of uncorrelated, not strongly correlated state on this atom. And the photon now is going to, because it's highly energetic, it's not going to just simply put the electron from this side to the other to create double occupancy. There is more energy than that from the photon, because I'm dealing with small gap. So it's going to put this electron into an excited state, and not necessarily this atom. This could be delocalized. It could be a band, But this atom now, whatever this atom may be, is going to be charged. And because I'm dealing with a Mott insulator charge, an extra charge in this atom is going to induce, is going to push this electron on nearby atom to go to, so this charge is going to push this electron now from this side to go to another one and create double utils. So at the end of the day, I end up with two doubly occupied sites, two whole states from this. So the point is, this electron that is highly excited, I don't want it to die into phonons, which take 10 to the minus 12 seconds for this. In the meantime, is it possible through mechanisms like that to allow the death into some form of death that I like? Why do I like this form of death? Is because I have now twice the current. I have 4 carriers, two doubly occupied sites, and 2 electrons, which through this voltage that I create across the interface, I can collect them through the leads. In momentum space, if I look at this perturbatively, this just creates 2 electrons, two quasi-particles, 2 quasi-electron states from the Mott band. And it could be that, or it could be because of the fact that the highly excited electronic state here in this other band can decay into, this is a quasi-particle, can decay into 2 quasi-particle, 1 whole state, or if the whole is highly energetic, and it can die into 2 quasi-holes and 1 quasi-electron. You can do it for this kind of decay, this death process. You can do, if you like, back of the envelope calculation using linear response. And what you find is that if you take some realistic parameters for materials, you find that the decay rate is of the order of 10 to the 14 or 10 to the 15 inverse second, which is higher by an order or 2 orders of magnitude compared to the other process of phonons. So I created a site that says, what's the advantage of these materials? Is because of the strong Coulomb repulsion, I can have death processes for this extra state that the byproducts of death are going to be useful for us because they create a higher current. This is the advantage of these Mott insulators. Now, if the material is wideband, so if I have a Mott insulator with a small gap, and a wideband, let's say half an electron volt gap, which I can always tune my Hubbard U to produce a small gap, and having a wideband of the order, let's say the band will be several electron volts, and this will be half an electron volt. If I'm in this scenario, then I don't need any other bands around, because when I have the photon coming in and photo exciting this electron hole pair, and the excitation will be vertical, because the photon cannot carry much of momentum relative to the electron, then I can have a decay process again, and I can be left with 2 holes, 2 quasi-holes and 2 quasi-electrons at the end of the day. So because of the decay of this highly excited electron here, quasi-electrons, this is a standard process, like this one here, in which this is the U, this Coulomb repulsion, the on-site Coulomb repulsion, which is causing this decay. And because these energy scales are pretty big, I keep getting, even though with, say, wave function normalization, because these quasi-particles can have small residue, I still get decay rates of the order of 10 to the 15 inverse seconds for this process, which is much faster than the decay process through phonons. By the way, there are papers. People don't realize this, they're dealing with Mott insulators, but there are papers where, and they don't really know which resin they should work on, but they have even reports of high efficient. These are all perovskite heterojunctions. You have, say, 1, 2, 3 on top of strontium titanate, or you may have manganites, which are Mott-like, on strontium titanate or silicon and so forth. And these are quite recent experimental reports. But as I say, the efficiency is not tuned because I think there is no calculations showing so far which way to go. And because I think there are questions on this. Let me just summarize. So, so when the solar photon is producing a very highly excited electron state or a hole state in a narrow band, narrow gap Mott insulator, that this excited electron lands in any excited state, but then it has to decay, and there are processes by which this electron can decay back to the upper Hubbard band by photoexciting, if you like, by exciting an additional electron hole pair. So you end up with two electron hole pairs, or multiple actually. If you have a very narrow gap, you can have n plus 1 quasi-electrons and n quasi-hole state in this decay process. And this increases the photocurrent. But I can also have a wide band, and then in this wide band case, it's just the strong on-site Coulomb repulsion that's causing the decay. So I think that effort should be placed in order to produce this in real practice, in real life. And then, by the way, recently there is significant improvement on how to produce oxide heterojunctions, and this is a growing field now, how to produce oxide, very atomically controlled oxide heterojunctions. Oxides is one class of Mott insulators. They don't necessarily have to, it's not, this is a more general idea for how to utilize Mott insulators. But oxides, peroxides is one particular class. And if you're interested for this decay rates and stuff like that, they're all clear high.
Let's see. Questions for Professor Manousakis. So let's see. Your basic claim then is the hope is to sort of realize Klimov stream. The hope is to use the properties of these Mott insulators as a way of actually generating multiple carriers at the junction. And you've done the calculations.
Utilizing also the fact that the Coulomb repulsion.
So your claim is that that's following directly, essentially from the Coulomb matrix element was simply the Hubbard Coulomb matrix element in there.
In one process, if the band is wide, that's going to be the one. If it is narrow, I need this.
You need another band.
Another band, and I need this other matrix element, this V matrix element.
So I guess the question is, have you initiated some collaborations with, for example, our DMFT friends?
Yes,
such as Gabi and or Christian.
Maybe they are better, but now I run at Harvard. I'm on sabbatical at Harvard, so I have my collaborators there. They're doing simple DMFT, but maybe Gabi can do a better job.
Okay.
Yeah.
Jim.
How about mobility? I mean, if you have to transport the charge, then one of the issues we talk about in cuprates is the difficulty of moving charges around if you have magnetic ordering, but then if I am in a paramagnetic state, then I got spin fluctuations.
Well, you see, nobody is telling me how thin these materials should be. So I can make them thin if I'm worried. Yes, this is a concern, right? But now, they do, the perovskites, the kind of matrix we have at the Magnet Lab, can do, then properties change. They do single layer, 3 layers, and then on the 3rd layer, it becomes metal. So you put 2 insulators together, and you get, on the interface, you get a metallic interface. So they can control layer by layer these materials. So we are not anymore at the level of just, laser ablation or any technique like that. We are at the point where we can grow these materials, at least first, and then. But yes, it's a concern. I don't. Yeah.
But in which are the materials that in this cited these experimental examples that you claim?
Well, we are right now trying to do, because we have an MBE that's we've beaten to death iron oxides for many years for magnetic properties. We are trying oxygen deficient iron oxide on, say, nickel oxide.
But the ones you cited, the papers that you cited.
The ones, as I said, 1, 2, 3.
Right.
On strontium titanate, there is also manganites on silicon and other materials, but I don't think those are the ideal materials. I think maybe strontium vanadate is, if I look at gaps, the optical conductivities, there are other materials which are probably more promising for this point of view. That I need a small gap to harness high efficient current. But in some of these studies, they even reported 80% efficiency. I don't know how reliable.
How much?
80%.
80%.
80%. But they define it in a very peculiar way. I think
Yeah.
it's a quantum efficiency I'm talking about.
Yeah.
Yeah.
I suppose, are there any other questions for Professor Manousakis? Okay, so I think the last part of this session is now a panel to discuss issues on energy. And I believe Alex was leading that panel, or David, I realize...
That's the first I heard.
That's the first you've heard.
I thought Daniel, in setting that forth, was that this would be a good time. And I want to throw out a couple of ideas for discussion, and then I want to encourage people to think of others. And let's see what we might put together in terms of an available set of options. One, and I've just written this, in fact, to Nate Lewis in the course of thanking him for his terrific and inspiring talk. One is clearly in discovering and developing emergent materials for sustainable energy applications. Now, there are lots of ways that we could imagine ICAM playing a role, but maybe the most interesting thing we could do is to try to make the case, going to the top, going to Steve Chu, that what we need, what the community needs, is the equivalent of Cold Spring Harbor, which has played an extraordinary role in molecular biology. We need the equivalent of Cold Spring Harbor for developing emergent materials. And imagine a faculty with our best and brightest, just in ICAM, it's an extraordinary range of people, we could do better perhaps, and a group of undergraduates coming from all over the world to learn how to make stuff. And starting them on a career of making stuff that is relevant to sustainable energy applications. So that's one idea. Another is, and these are more conventional and more obvious, a series of workshops on materials appropriate for application A, B, or C. Nate made a very strong case. Just think about the sun and forget about everything else, but that may not necessarily be our best approach. To workshops that can lead to research networks, and what ICAM can do is take any given research network and make it global. So there is clearly a significant add-on that we can bring to such problems. My second idea, or group of ideas, relate to education. It's very clear from listening to Nate and indeed just reading the newspapers that we are a remarkably uneducated country and indeed a global community in terms of the absolute importance of getting on with finding alternative energy sources and improving those that we have. And education can cover many different things. We'll talk tomorrow about a variety of things that ICAM has underway, but it can be anything from educating middle schoolers about climate change and its possible consequences, to developing materials for undergraduates, to having emergent materials, emerging universe festivals on a campus devoted to sustainable energy and its applications, to having a whole set of drop-dead exhibits on ICAM's online science museum, emergentuniverse.org, and I hope all of you have had a look at that. If you haven't, you've got your laptop with you, look at it right now, http://www.emergentuniverse.org.
Just emergentuniverse.org will get you there.
And these are just developing materials, working with teachers in all the school systems, et cetera, et cetera. These are all things that we're capable of doing. What is needed most of all, I think, are websites at every ICAM institution, every ICAM branch, devoted to what is happening on that branch on sustainable energy and connecting to each other and connecting to the best websites out there, using the internet as a way of communicating information and stimulating discussion and developing ideas. A lot of this is comparatively straightforward. My most radical idea, which I throw out, and then I will shut up and turn things over to Alex or Daniel, who chair the meeting, is that we ask every ICAM branch, we've got about 50, to come in with a contribution. Let's say we asked each one for $50,000. Okay? We then got $2.5 million as a slush fund, which we use for working the sustainable energy problem as best we know how. I'll stop there.
I guess I'll chair the session, but maybe I'll just add two comments. One is Nate made a very persuasive case that we should consider where we get the most possible energy. And that happens to overlap with what ICAM can do. And that it makes a great deal of sense to consider solar energy-based materials, meaning not just photovoltaics, although we've heard some fascinating discussions about those, but materials, advanced materials that could involve biological systems as well. Advanced materials which people in ICAM have worked on that could play a role in extracting energy from the sun. I think that Nate made a very good case for that. And along the lines of what David talked about, another thing that just occurred to me out of Nate's talk is if one of those wings of the Emergent Universe Museum, or one of the activities in a wing on energy and climate science, could be a kind of version of this thing the Energy Research and Development Administration put out in the 1970s, but it wasn't very good. It was like a flashing machine of lights where you controlled what the Earth's energy future was by making decisions about what was going to be going on in the present. Now at that time, the computer technology that was available and the presentation technology was pretty bad. But there's no reason why on the web you couldn't have people go through exactly the kind of exercises that Nate Lewis have gone through and our friend in Cambridge, David McKay have gone through, to illustrate what's necessary to solve this problem of simultaneously reducing the carbon dioxide emissions and not depriving us completely of the energy that we want to run our laptops, our phones, our cars, et cetera, and to have that available. And unfortunately, it looks like we lost most of the graduate students from the room. They all took off. But I'd like to hear what the graduate students think about that. Where are you? Come back! I think what that is maybe a signal of is that it is late in the day and that we may need to move on.
Graduate students have to eat early.
And the graduate students have to eat early. But
we did not invite them to dinner. That was our mistake.
That was our big mistake. But what we can do is we can perhaps go around the room and see if people have ideas that they would want to contribute to this discussion. Steve.
Well, one thing that I think we could do is maintain on the web page a literature source list. For example, I wonder how many people in this room know that the National Research Council has just released a whole series of very large reports called America's Energy Future, which cover a vast variety of aspects from policy through technology. And I suspect that we could fill the equivalent of several pages with very contemporary and relevant things to which people could turn if they knew they existed.
Right, well, what we do have already that we can easily add to, and I just want to mention this because I want everybody to give me their information about this, is we have a page where we can list anything on existing branches or other resources, easy to add to. You can add to it right now with links to courses at those universities,
The courses,
resources at those universities,
the next thing I was gonna
right,
suggest.
and also links like the ones you're talking about. For example, if you go to that page right now, you'll find links to the various Department of Energy reports on energy. You'll find links to some of the classes that we know about that are taught on some of our branches, but it's woefully incomplete. We can add to
I don't
that.
think we've been our course.
Then we should, absolutely.
For example.
Yeah.
Then there's another aspect on the very technical side that I think that didn't really get mentioned today. Simply developing the photovoltaic or cell devices is not really enough. And one of the big challenges is getting current in and out.
Right.
Interfacing,
Right.
interfacing small devices to the rest of the world is I think, a major challenge right now, and there are certainly some interesting possibilities. I could imagine, for example, thinking of using graphene as the conductor. Another possibility is this recent work on ultra-high conductivity and oxide-oxide interfaces. Things of this kind to match with the photovoltaic and other devices is something that fits very neatly into the technology and science of ICAM.
Absolutely. And we heard examples of that, I think, in some sense from Julia and from Frank's experiment.
Julia might be interested in doing that kind of thing.
Yeah.
Yeah. Although I think, by the way, this is one of the most unsolved problems.
Right.
Yeah,
Right, right. Even if you can build a multi-carrier generating device, how do you make sure that you get the charges to move in that device? Let's see. So Alex.
Well, getting back to the science for a moment, I mean, there are a number of themes that have come up repeatedly in the talks, and they are really scientific themes that fit very nicely with our issues of complex adaptive matter, emergence, etc. And I think they're themes that the community as a whole doesn't necessarily realize. So one certainly is the notion that any nanoparticle does not exist isolated in a vacuum, but is completely surrounded by either what you put on it on purpose or what it put on itself, and that one has to consider that whole system. The other, indeed, I mean, is this question of interfaces and getting charge in and out. Perhaps one could get together a set of these themes in some sense and help them focus not just our research, but research in general, to say, here are a set of overarching themes sort of powered by our viewpoint of emergence and complexity and whatever, buzzwords are, but here are a set of themes that come from the different things we're doing, including the DNA, etc., that are really across the board, and until one identifies them and perhaps works them into the materials we're interested in, one will be bound to be often disappointed because the materials are more complex than you think they are.
Thank you, Alex. Piers, did you have a...
Well, I've heard a lot about complexity today and a lot of simulations and heavy numerics, and I haven't really seen a lot of discussion about the simple questions, the simple principles, the notion that maybe some qualitatively new ideas might get us where banks of computers won't. And I think maybe a focus on what are the key questions, what are the physics and chemistry deep issues that we have to overcome would be very useful. I'm very afraid when I see these big numerical groups, and something also happens at my own institution, that students become chained to computers. They become very good at developing codes, and they don't develop a grasp of the physics and the chemistry and the principles. I'm very worried that we're moving we're not emphasizing the simplicity that comes out of complexity, and it's a fear of mine. I think we should be spending more time on talking about the principles and the deep questions that underpin, for example, making a good photovoltaic, than emphasizing all this effort on computers and simulation, which can be mind-numbing, particularly to graduate students.
I think you've rephrased my previous comments, perhaps more elegantly, for getting a set of basic questions, of basic questions for which computation may be a tool, but there may be other tools as well.
We might think about some workshops that help educate graduate students or even school on some of these issues, and energy-related materials issues.
But I don't think what you're saying is incompatible with what Julia was saying, for example. So I feel incumbent to let, as perhaps the most computationally skilled researcher in the room, to let Julia respond to that comment. I don't think she would disagree with what you said, but perhaps I should let Julia speak for herself.
Well, to some extent, I do disagree with what you said, but so in the sense that I think that you can use theory and computation actually to address very, very general questions. And the general questions goes to general principle and also general questions about materials. So it's not that you do computation just to solve a very specific material science problem. This is the last thing I wanted, the last message I wanted to give in my talk. But I think that at the end of the day, if you want to understand also what Nate was talking about, how do we do a device that really splits water?
Right.
You do need to understand the photoelectrode and how they are so alike, and how you can transfer charge. And there are specific problems to address that, in my opinion, computation will play a key role.
Right.
If you do this just by running the computer code without understanding anything,
right. That was what I wanted to single out. I mean, at the end of your presentation, you were stressing that it's important not to do that, not to simply run the code and get results, but to understand the principles that are underlying those results. And I guess one comment from my own experience on looking, for example, at DNA in complex environments is that sometimes it's helpful to be able to use the simulations a little bit in an experimental way. That is, you can't just simply think the organizing principles out a priori, that by using the simulations you can start to tease out some information that may point the way towards the organizing principles, and in that sense they can be useful. But I don't want to dominate the conversation. So perhaps is there anybody else? Ivan.
Yeah, today we heard a very broad range of beautiful research done here at Davis, in the renewable energy area, and I was wondering if ICAM could establish some sort of a network of current branch members of ICAM that have those strong research efforts. In Colorado we have just recently established Renewable and Sustainable Energy Institute. I guess pretty much everywhere people start doing something along those lines. Right. And as David mentioned before, the strength of ICAM is that it can convert any network to global network, and it might be a good idea to think about it. Apparently there is a solicitation from DOE for hub proposals, and if we would have this conversation, I believe it's in February, you might know about it.
Yeah, I mean, right now the two hubs that are being looked at, I mean, that's all. I think that there will be more hubs presumably next year, and you're right, we need to position ourselves, but the current call is, I think, not appropriate for us.
But I guess one comment about that is at David's urging, and I realize we have to collate all this and sort of synthesize this. But at David's urging, we did 2 censuses. Gosh, it would have been sometime, I guess, about the summer time. One of people of outreach efforts at all the different ICAM branches, and one of energy efforts at all the different ICAM branches. But even here, I'm finding out people who are doing things like some of the things Gabi's been doing recently I had no idea about, and Professor Manousakis' work I was unaware of. So the point is, we need to just keep working at this, and it will be an ongoing effort. But assembling the information...
Davis, that's certainly going to be a collaboration between ICAM and Mott.
Yes,
the energy
right.
part.
Yep.
As soon as we get back up to staff, that's
Yep.
a big thing.
Yep. So there's some simple efforts to collate, but I believe this could be an example of where we can really grow a research network out of this particular inspiration and have a corresponding, as David is suggesting, it's a very nice way of putting it, David, having a corresponding educational piece that goes along with it.
There is, to me, there is a fundamental question about this, namely, how many of our branches, I suspect most of them, have in one way or another a sustainable energy program which is intended to be campus-wide and somebody is running them.
Right.
Now, my guess, going around the room, is that probably 1 in 10 of us knows who that person is. And it might be that no one knows on their campus. I mean, Winston, I had the idea that Barry Klein brought in Martha Krebs to be that kind of...
Yeah, Martha Krebs is the executive director. It's really Jennings is the director, and the steering committee, Alex is on that.
Yeah.
Okay, and UC Davis
what basically happened was it came to kind of a grinding halt last year because of the perceived lack of money, so you'd call a meeting and nobody had come.
Yeah. So, but however, though, the chemistry department succeeded in recruiting 2 people, right? And I think it's a third is in the works. And the physics department, you heard Don Yu talk, right?
Yes.
It's a hard on the initiative.
But
yeah.
part of what's happening.
Today there's a degree of graduate program in energy is approved. Okay, and so that's
has the graduate group been approved?
Yeah, graduate group.
A graduate group in energy.
Yeah, in energy got approved.
The EGG, Energy Graduate Group.
Is that right?
Well, that's what it's called, yeah.
Oh, really? Well.
Efstratios?
I'd like to respond to David's question. At Florida State, there is an institute for sustainable energy established very recently, and they're mostly engineers. And I was very impressed, struck by the fact that there were even lawyers in this. And I don't know. I would ask you, what is their role in such an institute for sustainable energy? Somehow there are laws in various states and various countries which prohibit development of various grids for sustainable energy. And there were also engineers studying these grids, how you can. And I heard a talk at MIT by this guy who's claiming at Harvard, that he developed the internet, and he has devised a concept called enernet. So from energy instead of internet, energy. And he claims that his experience from internet is that the energy problem will be solved by distributing, because the computing so it has to be distributed in all forms, from geothermal to any form. Solar will be distributed. You have at home ways to harness all the forms of energy. So my point is that maybe we should involve here also people who are outside of physics or biology, engineers doing grids and things like that.
I guess maybe so, but I guess I have a tendency, not because of my own self-interest, which expands, my own interest to easily expand all those, but just thinking practically about what ICAM can do. And to me, it seems that we can do something credibly and practically if we focus on materials and the novel organizing principles of those materials that could be useful in this context, and that we can do something on the education side that could be very new and different. And on the international side, that's right. And I guess I'm a little, well, I think it's a good idea to perhaps, this is my own opinion, and I'm willing to disagree or have people disagree with me, but I think while it could be very interesting to bring people like that into workshops, it seems to me that our contribution has to somehow be rooted in the science and the education and outreach and engagement that goes along with that science. And that's where we can credibly make an impact on what we know something about. But that's my own feelings about it. Although it's been pointed out by David and Alex and others that particularly with bringing the Santa Fe Institute into ICAM, which has just happened, and our existing strength in social science work, for example, at the University of Michigan and at Kyoto University, that we could consider that piece of the puzzle as well, which is how do you shift social consciousness about this issue? Because it's clear that that's an enormous piece of the problem too. Elisa?
I would like to propose something much simple. I think nowadays many people that are making materials feel that it's important to go to this direction. And maybe it could have been in the message of ICAM some kind of guidelines for people that would like to enter this field. So I think it would be just something simple, but
So are you saying, let me see if I understand what you're saying. Are you suggesting that for young people wanting to enter this field, or perhaps for senior scientists wanting to enter this field, how do you do it? Where are the places to look for problems and questions? Is that what you're suggesting? Yeah. I think that's a great suggestion.
On that, Florida State, they had $1.5 million to develop a web tool by which you can hook up researchers across the state working on this renewable energy in terms of collaborative proposals, writing, and other things, workshops and like that.
So are you saying that this was a web-based tool for for file sharing, for developing proposals?
Right.
In principle, all that's on the ICAM website, but it's actually not utilized.
But they have some interesting stuff. Maybe.
Right. It's worth looking at to see how they did it, because if the key thing is if they've got people using it, then that can give us a cue about how to get people to use the resources we've already established on the ICAM website.
$1.5 million spent on
just that piece. Well, that's probably part of it. We didn't spend $1.5 million on that piece. Are there other... Oh, Jim Allen.
There is a person that is rather unique that we might try to draw into our efforts, and I'm thinking of John Goodman, who probably has his own personal best view of the emergence of materials.
I'm sorry,
anyone in the world.
John Goodenough.
Oh, yeah.
Because John's a guy who at one point made a deliberate personal decision to worry about energy. And out of that, of course, came lithium-ion battery. And he brought, and I was thinking of Pierce's comments that somehow you've got to think about it deeply and combine that with the kind of knowledge of materials that he had. I recently had him come to Michigan to give us a colloquium, and I thought he'd maybe come and tell us about lithium-ion batteries, but no, he wanted to tell us about his latest thoughts about quantum criticality and oxide materials and things like that. And I thought to myself as I listened to him, the guy's got it. He still knows more about materials than any human being I've ever listened to. And somehow, maybe we could draw him in some way to our activities on this front. I don't know. It's just a thought that jumped into my mind.
Jim makes a good point. ICAM really, at heart, is all about people. And the best resource that we have to offer to this enterprise are the people in our community. And they're self-selected, And as we know, when we meet the Board of Governors or Executive Committee or the SSC, they're also pretty independent and pretty skeptical. And the issue is, in a sense, identifying the network of people at our institution and others that should be in pretty regular communication about these issues. And then leave it to them to sort out what's the best format for doing that.
So
grassroots, that mixed with, I think, something we all agree, what we want to do. This is a minimum 20-year problem. We'd like to, at the very least, get the best and brightest of our undergraduates working away at that, because they offer, and not just in the U.S., but worldwide, because they offer the most promise, in fact, for coming up with new solutions that might make a difference.
Actually, David, it occurs to me, you may recall very well the founding meeting of ICAM, which out of which was now 11 years ago, last month, or 11 years ago last month. That's right. So I guess the question is, could we have another meeting like that, purely for the generation of ideas, which was focused on energy? That we would call together the people from the ICAM branches. We wouldn't put a call out to the whole world like we did at that time, but let's put a call out to the ICAM branches and self-select those people who want to participate. But what that meeting did was people weren't using PowerPoint then. Bring two transparencies with your idea about what complex and adaptive matter should be. So it really was from the grassroots up. We could attempt actually something like that, which throws it back out to the branches and back to our people. And it might be an interesting experiment to see what happens. Alex.
I agree. I think it's a great idea. There are two boundary conditions that are intrinsically different. One, energy is, on everybody's radar screen and on funding agencies' radar screen, were complex adaptive matter at the beginning of ICAM. Yeah, what's that?
Right.
And perhaps even now, yeah, what's that? So it's really going to be an issue of grabbing the attention of people who are busily scrambling for available resources in energy, etc. Because I think everybody realizes that that's, I don't think you need to convince the scientists that that's both a problem and a funding opportunity. So where ICAM really needs to help is sort of in the logistics and the support that makes spending one's valuable time more efficient to bring these people together. So I think we need to think about what sort of resources
Well,
we
You said there were two boundary conditions.
Yeah. So one is the concept that everybody knows energy is important as opposed to what is complex adaptive matter. And the other, which maybe is not separate, is that everybody's scrambling for money in that area.
Well, what we can offer is the usual ICAM offerings, I believe, which is we can offer workshops, and we can offer these awards for young scientists and for some senior scientists at a much lower level to try to nucleate interactions. But my point is, rather than trying to prescribe what those, we can place some constraints on the set of topics that can be discussed, some general constraints, but rather than to try to prescribe those topics from the top down to allow the group of ICAM people to innovate those topics and nucleate this network from the bottom up in the way that ICAM was originally founded.
I think that's a wonderful idea, Daniel. And just to be sure I've got it clear, you're not asking them to come in with solutions to sustainable energy.
No.
You're asking them the specific question that we raised at the start of this discussion. What is the niche or niches for ICAM on sustainable energy?
Right.
What are their ideas? And again, we could follow the protocol that we established for that founding meeting. Namely, your passport to enter the meeting was to deliver in advance a 1 or 2 paragraph statement or 2 PowerPoint slides.
Now we could ask for 2 PowerPoint slides in advance.
Spelling
Yeah.
out these ideas.
That's right. That's right.
And so, actually, for those of you who have any curiosity about our history, if you really work at the ICAM website, you can find those contributions which came from a really large range of people and some awfully good ideas.
Yeah. Yeah. Yes, Julia.
Yeah, still, I think that offering some, you want to have, suggestions from the people who, by the way, I'm not part of ICAM, so I don't know many of the things I'm talking about. But, for example, offering some suggestion, I thought that the connection between complex adaptive matter and energy that Alex gave in the talk was really good.
Yeah.
In the sense that the idea is, let's think about materials or materials properties we can tune to come up with materials or processes that are useful, for example, for harnessing solar energy or whatnot. This is a simple suggestion that one could give in thinking about what to bring in the meeting, which is already there.
Well, that's why I say.
You don't leave it totally.
Yeah, I don't want to leave it. I don't think it would be. I think it'd be a good idea to just not to throw that hypothetical ICAM meeting as wide open as the original ICAM meeting was, because the original ICAM meeting was sort of asking for a community definition of what complex adaptive matter was. I'm saying we should focus it. We should decide some areas, and then throw it out and see what happens. Some general areas, and then throw it out. I mean, the point is there are well enough defined areas that we can work in. But at the same time, we don't want to over-define. Yeah. So I think,
What, the definition that Alex had.
Yes.
No, I don't want to call it definition. I mean, the suggestion
yes.
about, let's think about how to tune properties, materials, so that we come up with processes and ideas on how to harvest, for example, better solar energy, or many other processes.
Right.
I mean, how to tune materials is, a lot of people write to that and use it as a buzzword. Where we're different, I think, is we have some ideas, related to complex, adaptive, emergent, all of which are concepts that have, a little bit more specific meaning originally in the physics community than just, good general buzzwords. And maybe we can use that kind of slightly more rigorous thinking to define perhaps promising directions.
Ivan, I think you had a.
I just wanted to elaborate a little bit on what we discussed previously related to undergraduate and graduate education. And I learned that in Davis here you just established a new program. I don't know if it's graduate or undergraduate.
Graduate. See, in Davis, all the graduate programs are interdisciplinary. Okay, and so there is a graduate group in energy established. Hopefully, it's very broad, not just science, but also involves policies, engineering, and so forth.
So, thinking along those lines, I thought that maybe one role that ICAM could play would be to develop some synergy between, programs of this kind, maybe undergraduate and graduate at different ICAM institutions, because I guess, those programs are being established right now, and there is, not that much experience. Curricula are being developed right now. They are highly interdisciplinary, as you mentioned. But, one way of doing it could be maybe applying for National Science Foundation IGERT award. And
yes.
I know that those can be multi-institutional. I don't know if, we could have international component, but...
that will be difficult because usually the support has to go to U.S. permanent residents or citizens.
But people can go abroad on it.
Right.
That's considered.
But and actually the call for, at least, for example, for Davis, the call for campus, you can only send out, I think, 5 from a given campus or something. And the